Let me start by thanking the organizers, Lenny and everyone else here, for inviting me to this very stimulating meeting. I would have never thought octopi could be such a contentious subject. I mean, mollusks are quite friendly, but nonetheless, I think this is a really inspiring new idea. So I have to sort of deviate a little bit from the title. Lenny sent a very important email that said, "You experimentalists, you hide behind these slides that you have kicking around in decks. Tell us something we really care about." So I'm not sure I will be able to do that, but I will try. So the idea is, what can we do with superconducting circuits today? What's the toolbox? Are there different architectures that are perhaps more well suited for the physics that we want to study in the near term, rather than thinking about necessarily universal quantum computation, which is somewhat far away? So that's really the more broad talk that I will try to give today, but I wanted to stay true to the program, so I didn't change the title. And I will get to it at the end. So let me thank the folks that do all the heavy lifting. This is a snapshot of the folks that sort of overlap with some of the experiments I'll talk about. In particular, there are 4 individuals that have participated heavily in these experiments. Makil Block, who is here, Vinay Rameshesh, who is also here in X, but in the AI branch, and of course, Shay and Emmanuel, who have moved on from the group. So I wanted to start with this discussion, and in fact, Brian had talked about yesterday that we're some generations away from universal quantum computing, and the objects that we have access to can be thought of as quantum simulators. So one way to think about this is that a quantum simulator is a poor person's computer. Perhaps another way to think about it, that this is actually quite a very rich system for a physicist. Right? So one can perhaps not concentrate on how far we are away from that. That's, of course, a very important and challenging aspect. But what can we do with the physics of systems that we have today? So I wanted to start off with this little image, which has a little tensor network inside. I'm paying attention, Lenny, to the audience, about a quantum system that may not have a lot of knobs. Okay, so this is a system that doesn't allow you to change a lot of the parameters, doesn't allow you to do very many different measurements. If you could do that, it would be your simulator. So this quantum system then evolves under some unitary time evolution. Yes, Daniel, I believe in this, so unitaries are fine for this talk. And you think about the system at time t equals capital T. So in fact, we can think about yet another quantum system. And this particular one, I've tried to shamelessly advertise things that have circuits inside, okay, that has a few more knobs on the outside, and it's got some speakers on the side too. So you can tune those knobs, and you can listen to different music that comes out of these. And the idea is this is now evolving in time. And typically, one thinks about, well, what's the toolbox in the case of superconducting circuits? So I'd give you examples where we have QUDITs, we have oscillators, and we have them in variable topologies. So that gives you a little bit of the basis vectors of how to play in this space. One typically then tries to initialize the system, right, to line up with this t equals 0 behavior, cook up some unitary operator which mimics closely the unitary you're interested in. And I'll give you 3 examples, something that's basically an analog interaction, something which is a digitization of something which can be continuous or analog, and something which is purely digital. Okay? And at the end of the day, you measure the system for things that you might find interesting in that particular setup. So in this slide, the first thing I want to say is that with superconducting circuits, all of these quantum systems, whether they're ions or atoms or NMR systems, each have very specific physicalities which allow different types of measurement and initialization. Okay, so in the case of these superconducting circuits, this initialization need not stop at t equals 0. And what I'm saying in code is that we have fast reset feedback in the system. So if you'd like to change your system along the way, that's a functionality that's available to us. And moreover, this measurement also need not happen in a projective fashion at the very end. In fact, we can weakly measure the system from time 0. We can measure it in the presence of the unitary also. So giving you yet another way to add a little bit of depth to what can be measured in such a system. And in particular, you can even close the loop with feedback, and hence the idea of putting these 2 arrows above and below each other. So at the end of the day, what do you end up with? We may end up with new ideas about physical phenomena. Okay? We will hope to end up with ideas about how errors propagate in quantum systems and how to control them. And of course, something about what really is the quantum technology that is compatible with having entanglement at the large scale. Okay, so I will work on these three. I hope the audience will be able to supply at the end. That was a joke. Okay. Let's dig a little bit into the superconducting toolbox. Okay, what are the pieces that we have? Now, one of the comments I want to make here, the three exemplar cases that I'm going to talk about, was really us trying to expand our Hilbert space with limited components. Right? The idea that you have finite coherence time, you have finite connectivity in your sample, what are tricks that we can play in the system to give us a bigger Hilbert space? So that's the overarching comment. So starting first with, well, what is fundamentally a qubit? In our case, it's a piece of metal that is used, a superconductor, that's used to make a tunneling junction. The tunneling junction is a nonlinear inductor. You shunt the inductor with a capacitor, you get an LC circuit. You pick the parameters right so that the spacing in your LC circuit is of order 1 to 10 gigahertz, say. This LC circuit, of course, is coupled to some complicated environment, which causes all flavors of relaxation. And here's an image in size scale of what we're working with. These are aluminum tunnel junctions. It's not the junction which is moving, it's the projector. So, no, I mean, the junctions jump around also. I'll show you that, but not in this case. So here's, in fact, a submicron tunnel junction. And I wanted to put up some numbers in some dimensional way, okay? Because this drives the idea, well, what are we trying to build? Do we have the technology to build the 1 million qubit machine? That's a very different question of thinking about building the 100 qubit machine that may be very near term and rather plugged into physics experiments. So not knowing how to build the 1 million qubit machine, I wanted to put up the numbers. Well, what are the limits of aluminum, right, as a metal, right? And what are those fundamental constraints that set the limits today? So if you take a qubit, in this case, the minimalistic form that has one junction, one capacitor, put two ears on it to make it basically a dipole that radiates, you can measure times close to almost order of 1 millisecond. Okay, so that's quite a long time. Given the gate time in such a system, for single qubit operations is of order 10 nanoseconds, a 2 qubit operation order 100 nanoseconds. So that gives you the scale of if I was really able to capitalize on the material science that I have today, that's the number of ops I should be able to run. So another interesting and important time is what is the coherence time of an LC oscillator, just a cavity that you make. If you make something out of bulk aluminum, a box, or even niobium is even better, you can get about a second. Okay. Again, translating that into a chip, which is flat, is not trivial at 1 photon, but it's telling you that these are numbers that are achievable in certain settings. Okay. So let's go beyond 1. A few years ago, we said, well, let's try to build 8 of these in a ring. Okay, and we like the ring geometry because, in fact, it allows you to couple without having swaps along a linear chain. Right? We are starved a bit for coherence, so it's nice not to have to flip all the elements in the chain to couple the two ends. You put 8 of them in a chain. T1s, T2s, T2 stars are shown here. You get of order in this particular generation of device, average 60 microseconds T1, close to 80, 90 microseconds of echo time. These numbers are closer to about 100 microseconds at the moment. And in fact, if you don't couple the qubits, we're well above 100 microseconds, telling us we have not learned everything that Maxwell taught us just yet. Okay. What are the limitations? I gave you these much larger numbers, and somehow I've sort of deflated the bubble, give you things that are much more short-lived. Well, these are not bulk superconducting structures. They have surfaces, they have interfaces. And in the poor metrology techniques that we had a few years ago, we were just putting drops of water on the surface to see if we had monolayers of oxide. Because in the 70s, folks told us in the semiconductor industry that each monolayer changes the wetting angle of water. So in fact, we were able to target where the oxides were in double T1. Okay. But then we also had this problem. Look at 4 qubits that are next to each other. The colors are not rendering great here. But in fact, these are the different coherence parameters. And they're spread around, and they spread around in time also. So your quantum computer, in the true quantum sense, may be working at this moment. It may not work at the next moment. Okay. So how do we go beyond this? Well, we paired up with real material scientists, started to look at this surface. Okay. So here's now TEM images put together from folks at LBNL. Here's the silicon substrate. Here's the dark niobium metal. And there's a very healthy layer of niobium oxide on the top. Niobium oxide as imaged here through various X-ray measurements, is not stoichiometric. And it has of order half a dozen different flavors. Some of them, in fact, in their amorphous configuration can be magnetic. So you need to close the loop on what is the effect of the oxide, how do you get rid of it, and how does it affect coherence. This is something supported through BES at the DOE. So we started playing with this surface. So shown in gray are the Q factors of resonators that we would make in this 8-qubit chip, hovering around 1 million here. Oops. Hovering around 1 million here. And then we would try different things. We use self-assembled monolayers underneath the metal, above the metal, trying to sort of change that interface. And in the simplest case, we simply tried to etch some of this niobium oxide. If we start putting in these SAMs, shown in yellow and this sort of reddish color here, you can see if we put them in the right spot, we simply increased the Q factor to 2 million. Wrong spot, we actually decreased it. Okay, did a bad job at it. With etching now, even in fact, the easiest etches that we're doing were well above 3 million. So we're starting to make progress on improving this coherence time, at least in factors of a few. What about the junctions? Here's a TEM through a cross-section of a tunnel junction. It looks horrible, right? It's not flat, it's got curves, and so on and so forth. There's elemental analysis done now on 5 different spots on this 30 nanometer scale bar, telling you that your aluminum and oxygen content, in fact, isn't Al2O3. Okay. What does that mean for making large amounts of junctions? Well, you need to make large amounts of junctions to test that. So here's a clean room that we run in the lab that's class 10 that produces 6-inch wafers of these devices in 2 days, and that's the only thing this clean room produces. So that way we have some tight control over the process. So automatic probing. Graduate students have been relieved of measuring these 3,000 junctions at one time. So we put in wafer after wafer, different processes. And graphically, you can see this was a plot across this 6-inch wafer. The color code tells you the spread in frequencies that we were targeting of our qubits. Okay, so here are the 8 qubits in the ring, and you see it's a very wide distribution. Right? That was the variation in these junctions. 36 wafers later, we can get it down to something that's significantly narrow. And in particular, you can see the little curvature there. That's intended so you park the qubits at the right positions. So the technology is getting better to put together, at this point, of order 100 qubits with good control. How should you wire them up? If you want to do the surface code, it's true, you put them in a square lattice. Okay. But you may want different connectivity, in particular for problems in high-energy physics where you have a higher coordinated graph. So this QPU that we're going to put in now, courtesy of Roger Luo, who joined our group from Oscar Painter's group recently in Caltech, is called the SpiderNet. Okay. And this has a much higher level of connectivity. So shown here, it's basically a bus which can be reconfigured in time, dynamically. Okay. And in particular, this is the EM simulation, if you like, where it's hard to see again, but we've extinguished coupling between 4 of the qubits and have it in the others. So depending on the pulses you put in, you can have different levels of connectivity. Where does it go? I have 8 dilution fridges. This is by far the biggest one at the moment. It has 2 mixing chambers. It's wired up on day 1 for 128 qubits. So the wiring problem is also a big one, right? Feynman says there's lots of space at the bottom. There's not a lot of space at the top. Okay. We took the attitude, well, if we can learn physics with 128 qubits, I can brute force 128 qubits. No multiplexing, nothing special, just multiple wires per qubit. This is 1.5 meters or so in diameter. So it's wired up. We partnered with a local company to actually put together this cold stage, which is here in 4 little plaquettes, because the idea that we had was, even if I were to build a 128 qubit machine, the Hilbert space would not be 2 to the 128. So it was certainly better to have different designs in 4 pockets with 32 qubits apiece. The control electronics, this is 64 channels shown here, all synced to within 5 or 10 picoseconds. So commercially, that technology is there. The High Energy Physics Division of the DOE is supporting development of our own FPGAs. This is work done at LBNL, where you have optical interconnects between these controls. And in fact, they're being used for randomized benchmarking just fine. You can get up to 1,000 channels if you need it with this technology. And of course, there's human capital. Right? So you need all the folks to go ahead and run those physics experiments. So 3 experiments. First one, analog simulation. So the motivation here, 2015, was, well, the transmon is a very simple qubit. Let's imagine we encode information in a chain of them. Okay. You get more knobs, more handles, bigger Hilbert space, etc. So one thing I do want to start off with is this was a very simplistic analog simulation. There's been a lot of work in the community. Alicia Colares here has done beautiful work with arrays of bosonic cavities. So indeed, that is a whole field that we cannot review at the moment. But I wanted to give you a flavor that we can kind of look like atomic physicists also if we want to plop down qubits as atoms. Here's 3 of them. Okay. 2 of them are tunable. 1 is fixed in the center. Bose-Hubbard Hamiltonian has some on-site energy, right, for each one of the particles. Then you have some hopping between your pockets. And then you have some pairwise interaction within each pocket. Here's the system of transmons, tunnel junction here, capacitor here, LC circuit, coupled by another capacitor. Okay. These things are paddles, so in fact there's some capacitance to their nearest neighbors. The Hamiltonian for this transmon is written here. Right? This is the interaction for putting 1 excitation on your transmon, B dagger B. These are the bosonic modes of your oscillator. This is the coupling, so these are also the bosonic modes, but between neighboring oscillators, B1 and B2, coupled with some exchange constant J. The transmon is an interesting object. The anharmonicity is negative. So in fact, if you wanted to put 2 excitations, you have 2 choices. You can have each transmon or site with 2 excitations, or you can put them across 2 of them. And in fact, since the anharmonicity is negative, it's a bit easier to put them on 1 site rather than 2. So if you wanted to distribute this energy between 2 sites here, B dagger, B, and B, in fact, it's a positive interaction. It costs you energy to do that. So this is, for the experts, this is a different limit of the Bose-Hubbard Hamiltonian than you normally get in the atomic system. And that's because of this negative anharmonicity. You take the spectrum, it works. Okay, so that's the spectrum of this 3-element Bose-Hubbard chain. We have the ability to change the frequency of the qubits, so you can see all sorts of interesting crossings that come in and out and so on and so forth. And you can count modes. There should be a ground state. There's the 1 excitation manifold in the chain, the 2 excitation manifold, so on and so forth. Right, they're all there. You can figure out all the places where they cross and anti-cross. You can also look at all the dynamics. This is also interesting. If you excite something in this higher element, what's the decay pathway to the single particle subspace and what have you. So this was cute. You could shelve quantum information for long periods of time in such a system. So just to give you an example, that this is an analog simulation with some knobs that you can run. And in fact, you can increase the number of qubits by very many if you wish. OK. Second piece. First piece, I increased the density of the Hilbert space by adding more qubits. But I told you we also have oscillators. And in fact, within 1 cavity, it's possible to store very many modes of the photonic state. So this was an experiment where we would use the different photonic states of a cavity mediated by 1 qubit to give you a reasonable Hilbert space. In the language of quantum information, we try to simulate this model for topological structures, in particular the Su-Schrieffer-Heeger model. This is a canonical model for 1-dimensional topological insulators. It's used in chemistry, many places, et cetera. But the gist of it is it's a model that has block bands that have spin texture. So in the trivial state, as you traverse this Brillouin zone, you pick up no phase. In the non-trivial state, you have a phase flip. Okay. So the idea we had was, well, could you simulate this type of physics? Could you come up with a system that would traverse this Brillouin zone and show you very definitely this topological character? So the experimental protocol was based on a quantum walk. Okay. So here's the mathematics of the quantum walk. You start off with a particular state. You toss a coin, which is basically the equivalent of putting a pulse on a qubit. So here are the lattice that you can do your quantum walk on. You start at time 0 in this particular state. And then, depending on the result of your coin flip, you translate with this translation operator either here or here. And you flip the coin again, you translate again and again, so on and so forth. So there's an operator for rotations, there's an operator for translations. You put them together and exponentiate, you have a digitized version of some Hamiltonian that could be of interest. Okay. You can express this lattice translation in reciprocal space, and then you can, in fact, map out very easily that this type of digitization corresponds to a spin-orbit coupled Hamiltonian. Okay, so that's the flavor of quantum simulation we wanted to run. So again, we had 1 cavity that in fact had of order 12 photonic states, different amplitude and phase. So these are typically plotted in this phase space plot with the imaginary and real parts of the coherent state. You displace the cavity, right? That's initializing the quantum walker. You put a pulse on the qubit, and depending whether or not spin up or spin down, it will move around this cavity on a circle, one way or the other way. Okay, so there was the circuit. You would prepare the thing, you do the quantum walk. And what I wanted to end up here with was the following. You do the quantum walk for these two different topological states, and you measured the state after the measurement. You made sort of this classical type of measurement with a Q function distribution. You couldn't tell the difference between those two topologies. Not shocking, because topological character is not so easy to get at. So what we did in this experiment was a bit different. Let's not use coherent states, let's use Schrödinger cat states. So this is how we actually did the walk. You started off with a cat, right? You have one piece of your displaced walker, the other place at 0, and I shelved this state into a higher level f. So it just stays there as a phase reference for whenever I need to actually make a phase difference measurement in quantum mechanics. Then I let the system walk, and I bring back and compare to this other leg of the cat. And that's sort of what this graphic is showing you. There's a walking cat and a parked cat. And there in the Wigner function, you immediately saw the Zach-Berry phase coming out very cleanly. So what I wanted to illustrate with this is that measurement need not be classical. You may want to use things that are very quantum mechanical in this particular domain. And of course, this audience is no stranger to that with teleportation, which we'll get to in a moment. But this is in the more condensed matter domain. So in the remaining 10 minutes or so, let me go to the advertised topic of scrambling. So you have seen this circuit many times. This community has come up with this circuit. I need not repeat it. Chris Monroe, of course, discussed it also in the morning. The difference for us is that we wanted to use 3-level systems, in which case you can have your unitary bridge just 2 of these QUTRITs, okay, rather than having ternary coupling that was here. So the circuit, you would put in an input state. Your unitary would mimic Clifford scrambling for us. You would, of course, have the qubit already in some sort of memory via an EPR pair, reverse the process, look at the input and the output via teleportation. So your EPR pair looks like this, of QUTRITs. You spin one system. Your scrambler, in this case of a Clifford scrambler, takes 2 inputs and just swaps the indices in a way which spreads information in your density matrix to give you scrambling. Okay. So there was a statement. Is Brian Swingle still here? Yes, yes. You made this statement about experimentalists not having this quintessential figure, right, in their talk. So I've added this figure in this talk. As you can see, experimentalists, we see in color. So I added color to the figure. Now, if I understood Sandu Popescu's talk correctly, I need one more experimentalist to do this, and then we can send a message to you, Brian, a posteriori, that we have added the figure. Okay. It's a hard experiment, as Chris was saying. So you start off by making the EPR pair. So you start off with the general state. You put a rotation of this particular angle, and that forms the state 0, 0, 1, 0, with weights 2/3 and 1/3. This is real data of your Manhattan plots. You put in this combination of pi pulses along y and along x, right? And you're able to move these 2 elements this way, and this one element of the matrix here. And that gives you 0, 0 plus 2, 2, again in this 2/3, 1/3 weight. And you apply yet one more set of pi over 2 pulses, and that gives you the state here. 0, 0, 1, 1 plus 2, 2 with 94% fidelity. Okay? So that's the first part, to generate this EPR state. Now you want to scramble. Okay, so you have to come up with the unitary. Unitary is tricky. Okay? One would think you simply go ahead and put pulses and move things around in this Clifford set. But I think it's become quite popular to talk about this Floquet dynamics, also in these systems, as we've heard in talks yesterday. So Vinay and Makil came up with this kind of gate, thinking about dynamical decoupling, which is rather similar actually to what you do. If you think of 2 of these sites, they always have a ZZ type interaction, which is on. After all, they resemble dipoles. If you go ahead and then think about adding local X gates on each QUTRIT, right, and you combine these 2 operations, you will actually get this scrambling operation if you have the right phases. So indeed, this scrambler is decomposed into the following. You run the ZZ, which is already running, normally in terms of your crosstalk, and then you apply these very carefully oriented pulses in between locally. And this realizes a pretty good scrambler. Okay. Does it work? Seems to. So in this plot, we put in certain elements of the poly set and look at what comes out. If you put in a local gate, you get a local gate at the output. Right? If you put in something that generates entanglement, then you see weights at certain parts of the two-element Hilbert space. And if you run this sum gate, then indeed you should get scrambling. This is the theory, this is the experiment, okay, in process tomography. Okay. The space grows fast, right? So in your spin 1 system, there's 81 of these things that you need to run. But luckily for our superconducting qubits, they have short coherence time, but they run very fast. So to take this plot is only 1.5 hours to do all of them. Okay. So you put all the pieces together, readout fidelity approaching 2 nines, if not greater, for 3 states. It's certainly better for 2 states. For 3 states, a little bit harder. You do the EPR creation as I talked about. Then you have to do it at the same time, which is even harder because you have crosstalk between the elements of your chip. Run the scrambler and then run teleportation. So here's the real circuit put all together. It's heavy for us. Right? It's got a bunch of gate operations for sure, so the fidelities all have to be optimized for making this work. Scrambling, by the way, also doesn't allow us to cheat. Right? You can run an algorithm and say, I ran the algorithm, and the result is very bad. Unfortunately, scrambling, you have to be above some fiducial threshold to say that quantum mechanics actually exists. So we ran it, but running it good or running it well took a long time. Here are the Gell-Mann matrices. You put in those 9 possible Gell-Mann matrices, you look at what comes out. What's shown in the shaded part is the experimental result. The dashed line is what you'd expect. So indeed, we start to get the right parameterization here. And in particular, you can look at these elements of the 2 design, where you put in these 12 metrics that we put in, and you look at the fidelity of this teleportation. When we scrambled, on average, we have 56% running the whole thing. When you adjust the phases so that you're not scrambling, you measure 1/3, as you should for a 3-level system. So this is sort of the state that this teleportation experiment is in. And what we hope to do is, again, to come up with different circuits with different topologies to solve problems that are of mutual interest to all physicists and chemists and high-energy physicists and what have you. So the TESTBED program, I gave you some snapshots of it. The idea is to stand up something in one piece that has all of these elements of the stack, and also partner with the community with different processors, different technologies, different algorithms, etc. So that's the overall mission of this particular DOE program, sponsored by Oscar. And I stop here and take your questions.